Thank you, Dave, for inviting me to give a talk. So it's not going to diverge too much from what you heard. I'm just going to highlight a few more use cases for simulated earthquake ground motions, which I've worked with over the past year, initially as a postdoc, as a consultant, and now as a professor with my students as well. So without wasting too much time on building for the motivation, because we've been hearing about it all day, locations specifically very close to active faults that are at the risk of having large and rare earthquake events are difficult to analyze. So the performance of infrastructure at those locations is difficult to predict or assess. Yeah, so for us, the most important goal is understanding seismic risk to structures that are very close to the faults, that are at the risk of experiencing large damaging and rare earthquakes. So large, that's why they're important, and rare, that's why they're difficult to assess. And so the rarity of observations for those types of locations, those types of structures, is the main reason why we use these simulated ground motions. So without spending too much time on explaining how the simulations are conducted, we heard about that a lot. Really, kind of my role, I like to think, is if you're looking on the earth science on the left all the way to the engineering at the right end, I'm kind of in the middle, leaning more toward the engineering. So I try to use these ground motions to think of applications in engineering analysis that can benefit from these simulated ground motions. And they fall into two categories that are not too different from what people talked about before: improving our understanding and our ability to predict seismic hazard, and identifying effective approaches to select representative earthquake records for seismic risk assessment and for particular engineering analysis applications. So generally, if you kind of look, again, from hazard all the way to structural analysis from the left to right, there are two kind of basic, fundamental use cases you can think of ground motions, simulated ground motions, where simulated ground motions can be used. You can either supplement or replace recorded ground motions with simulations, or you can represent the seismic hazard itself at a given location using simulated ground motions. And so we've looked at some of these in both the different types of use cases. And I've worked in the past year with a data set that's kind of a preliminary data set to the Bay Area ground motions that have been just shared recently. So this is a study from last year on an earlier data set. And so the first use case is pretty easy: supplementing simulated ground motions, supplementing recorded ground motions with simulated ground motions, right? So how do they do? So if we have the seismic hazard and we're going to select ground motions to match that hazard, but we're going to do it with real ground motions and with simulated ground motions, does it work? Is it the same? Does it give us the same behavior? And this is what we're looking at here for a magnitude 7 event at a distance of 1 kilometer, so very close to the fault. So we're seeing on the left real ground motions, on the right simulated ground motions. Do they do the same? Well, they look similar, right? But for engineers, we want to see if the building response would be the same to both of them. And it turns out it is actually quite similar. So if we assess, we're looking here at cumulative probability of maximum inner-story drifts and floor accelerations on, I think this was a 12-story building, reinforced concrete. So we're actually seeing that those response distributions are very similar between real records and simulated ground motions. And we've used this in a lot of different other cases and seen similar results. Now, the little bit tougher challenge is, can we actually use simulated ground motions to represent site-specific seismic hazard? And what we're looking at here is one of the ROTE 50 representation. So this is orientation-independent representation of seismic hazard at a site for magnitude 7 and distance 1 kilometer again. And we're getting the red here as a representation of the empirical ground motion prediction equations, whereas the blue is actually just coming from simulated ground motions. So there were a lot of talks about this earlier. The models, are the models right? Are the simulations doing better? So I'm not going to go into that again. But what is to know here is, I think to me, there are two phases of looking at these ground motions over the past years. The first with kind of reality checks against observations, against recordings, and also against empirical models. And now that we have more confidence in those simulations, we're actually looking at what are the simulations capturing that is not captured in the empirical models. And so, to me, some of what we're seeing here for this very near field location is, for example, higher spectral intensity predicted by the simulated ground motions. So it is something to consider. Again, the more observations we have, the more development in the simulated ground motions that we get, we're going to be able to better assess those differences. But the question is, if we can now use simulated ground motions with some confidence to represent seismic hazard, at least for some certain cases, what else can we learn from that? How can we use simulated ground motions to, how can we use this new, maybe improved representation of seismic hazard that has all of these interesting additional site-specific effects, directivity effects, all that stuff? So one study that I've done over the past year was actually looking at the so-called co-seismic offsets or displacements, sometimes called fling step. So this is kind of basically due to the movement of a fault. You're looking like here at a strike slip movement, and that movement results in kind of a permanent shift in the ground. And the simulated ground motions can actually help us understand a little bit better about where and when do we see these displacements, their magnitudes, and also assessing their effects on structures because they're typically associated with large pulses. So what that looks like is that you have the fault is shifting, and then you end up having this kind of permanent step in the ground displacement record. And it turns out this is very difficult to obtain from real ground motions because of the way we process the data coming from the accelerometers. This permanent offset actually has to be removed from your real ground motions. So that makes this very difficult to assess and understand this effect from real records and to know how it might affect infrastructure. And it turns out also we see that this permanent step, as you would expect, corresponds to a big pulse in the ground velocity record. It's different than the known directivity fault pulse, which is kind of a two-sided pulse. This is more of a strong one-sided pulse that corresponds to this step. There's something here from the Zoom meeting telling me something. It says that I'm muted.
Okay.
I hope that doesn't mean that I was muted the whole time. I hope not.
Yeah.
Okay.
Keep going.
All right. Well, we'll pretend it's fine. Okay. All right. So there are two things to think about here. First, this big velocity pulse, how does it impact infrastructure? And do we need to account for that? Because we think about directivity pulses, which appear in the fault normal direction, but a lot less studies, a lot less people have looked at this one-sided velocity pulse that for strike slip event appears in a fault parallel direction. And then second, how does this cross-fault displacement affect structures that are crossing the faults? So this is another a very important thing to think about. Okay. All right, so how are the ground motion simulations doing with respect to this fling step, with respect to displacement? Before 2022, I would tell you this was a very difficult question to answer. Thankfully, when we were working on our paper, this NEST 2.0 database was published, and it actually has, the authors have conducted a special processing of some real ground motions where they can extract this permanent displacement. So we're actually able to compare our simulated ground motion data set against real records, and there are also some empirical models that try to predict this magnitude of the permanent fling step. So I would say overall, it's doing very well. There are a lot of differences that we tend to see depending on the shallow rupture characteristics. And so it's kind of difficult to do this without comparing rupture event by rupture event. For example, we know that having these slip patches, especially when they're positioned very shallow, they actually influence the magnitude of this permanent displacement a lot. So we're seeing here the colors may be not that clear, but at the top you have closer to about 2 meters of offset, where at the bottom you're a little bit less than 1 meter. So, and those correspond to different rupture realizations where the top one has this big patch of large slip. So you see this clustering of the permanent displacements around that area. We're also able to compare what the shape of ground motion records look like that have these big permanent offsets and the pulses associated with them, which was not possible to do with real ground motions. So now we're able to get a whole suite of ground motions of a magnitude 7 at 1 kilometer, and a large group of them have permanent offsets, so they're typically fault parallel, and a large group of them don't have a permanent offset. They're typically fault normal, so they're still pretty intense, but they're not associated with this fling step. And so we're able to see that ground motions with strong fling pulses actually tend to have higher spectral energy, whether it's at the long periods only and sometimes a broadband range of periods. So that tells us that at least some of that effect of those pulses is reflected in the ground motion spectral shape. So this is a good start, right? So that means if we do our ground motion record selection and match the spectral shape, as long as we have the right target spectrum, do we end up doing well representing the effect of that fling pulse? So that's what we looked at. And we found out, well, two important things. We found out that this fling pulse is actually really important for tall buildings, and especially for representing the residual drifts in tall buildings. So we looked at, I think the not super tall, looked at a 20-story building, but it turns out for the residual drift of that building, representing the effect of fling was really important. And the second important thing that we learned is that when you select ground motion records based on the full spectral shape, you may actually end up underrepresenting or not counting for those fling effects properly. And that is represented here on the right by the distance between the red, which is the selected ground motions, versus the blue, which is our target. So that distance is kind of large. Whereas if you actually prioritize the long period component of the selection, so you weigh more heavily the spectral ordinates that are in the long periods closer to the period of the building, you actually get a better representation of the building response. So you see the behavior from a selected ground motion is close to the targets. And this is specifically the case for residual inner-story drifts, but we've also seen similar results with inner story drift as well. So now we're just getting the new data set, and we're starting to work with it and look at what do these fling step magnitudes look like in the Bay Area simulation. I have a PhD student who's beginning to actually work on understanding how are these fling step magnitudes going to impact structures crossing the fault. So now we're looking at distributed infrastructure, including bridge networks and also lifelines. All right, and now looking forward, so another interesting area that we're starting to work with is looking at how we can make the most out of a small number of what I'm going to call expensive simulations. So there were some talks earlier about how many of these scenarios do we need? Can we run more? How many make sense to use in an engineering analysis? And not everyone, and for every location, we're not going to be able to run a large number of simulations. So the goal of some of the research I'm doing now is looking at how can we reduce uncertainty at a tractable computational cost. Or another way to look at it, if we have a fixed computational budget, what's the best way to select the most representative scenarios? So it's a very challenging question, and we're only just beginning to look at it. So on the left here, you have some of the data generated by my PhD student as well, looking at if we take the 50 realizations of ground motions and we assume that is our full population of possible realizations for this magnitude 7 scenario, which they're not, I'm sure there's more, but let's assume that's the ground truth for now. And now what happens if we go and just take samples of 15 realizations at a time and get what's the median and standard deviation or variability around the median in each sample. So we're emulating the idea of someone maybe going and deciding to run 15 scenarios. How much variability would they expect to see? And it turns out quite a bit. So of course, this variability goes down as you increase the number of realizations, but our goal is to actually think of how can we improve the way we select scenarios so that we're actually able to better represent the properties of what we call the full population or the ground truth. So in this case, we're looking at this red line here. You're looking at the sample median with the variability around it, whereas the blue line, you're looking at the median from the full population. And so the question is, how do we pick samples that would actually be close to the ground truth or the population properties? And so this is the question of what I call optimizing the design of earthquake scenario experiments. And when we say experiments, we typically think of lab experiments, but there's been a lot of literature on actually working with computer experiments and optimizing the design of computer experiments. And so some of the questions we're looking at are related to how we can design representative rupture scenarios. What is the representative rupture scenario, right? How do we determine that? I think John Day earlier spoke about doing full-scale exercises, right? So those exercises for a regional risk assessment, they typically take a small number of scenarios, maybe even one scenario. So which scenario is a representative scenario? How do we select that? And more importantly, looking at it from the end, from the target application. So if your target assessment goal is for a bridge network versus a critical building facility versus a transmission line, can you use that target engineering application and kind of backtrack to decide what are the most appropriate scenarios for you to select so that you're getting appropriate answers for your applications? So with that, I will just like to acknowledge all the funding. My work over the past few years have been done at Oklahoma State University, an exponent. It's been funded by USGS and OSU, in addition to direct funding from projects from Dave's project, funded by the DOE. So thank you. I will stop here. There's a QR code if you want to go on my website and look at some of the papers and publications on this. And I'm happy to take questions. Thank you.
Thank you. Any questions? Any question from the floor for Maha?
Yeah.
Did you take also a look at the amount of offset variability, not just the external offset?
Just a second.
So
Repeat the question.
Sure. When you were looking at the Hayward fault, did you look at the amount of uncertainty in the fault offset, the actual primary and secondary offsets, as well as the extra velocity, sort of this pulse?
yeah, so the study that I did was on a data set that's prior to the Hayward fault data set. So it's done on like kind of a generic fault. And we did look at all sorts of variability. So I'm happy to direct you to the paper. It looked at a lot of variability in the ground motion shape, but also kind of looking visually at the maps at what changes, what variability do we see in the magnitude of the offset from one realization to another. And it's really closely tied to the location of the hypocenter, the rupture characteristics in the shallow area, having these slip patches. So all of that stuff is factored in. What we didn't look at yet, and we're beginning to look at now, is what happens to structures that are crossing the fault because of this extra displacement. So this is what we're beginning to look at. So we want to put some bridge over the fault and see what happens.
Why don't you use Bay Division 3 and 4 to HHE Aqueduct? They spent $100 million fixing that pipe crossing the Hayward Fault. $100 million. And it's in a tunnel now, and it had to deal with all these uncertainties and ground motions.
Yeah, give me that, and I'll use it. I'll simulate that, of course. Yeah. Thank you.
As you looked at this, do you understand exactly what parameters in the Graves per target rupture model control the rise times for displacement? Because that's a critical value.
No, I can't say that I do. No. So I think the thing that we looked at was how the slip patches influence those fling displacements,
Yeah.
and that was the
It would
most
be
dominant
interesting
thing.
to understand what exactly controls that rise time.
Yeah.
Because you can imagine the base of the building is moving over very rapidly, and how rapidly matters, right? And so just understanding how that relates. Arvin's raising his hand.
Yeah, I was gonna say if ARPAN generates more simulations, I'll definitely analyze them.
We assume 4 seconds from 0 to maximum displacement.
So what it's working. So I think what's controlled the overall rise time is the magnitude of the earthquake, first of all. But we do have some kind of variability into the rise time within the rupture itself. And it tends to be a little bit longer when it's in the patch. Okay? So,
Because of the amount of slip that's occurring.
Yes.
in the patch.
yeah. And that's why usually the ground motion generated with ruptures with slip patches tend to generate higher ground motion in general.
So are you saying that
In intensity.
so that would or wouldn't affect the amount of permanent displacement?
Say
Changes
again?
in the rise time, or are you saying that the rise
Changing-
time is just going to be tied to
It's
the
not
magnitude?
going to change the permanent displacement.
Okay.
It's going to change the amount of velocity or acceleration that is attached to the dynamics of that ground motion at that site.
So what will
And usually it could be really high, both in terms of permanent displacement, but also acceleration due to the fact that you are close to a patch.
Arvin, I'm more wondering about the slope of that rise time. The slope of the rise time as opposed to the amplitude of the rise. What controls the slope of the rise?
Well, like I said, we use an empirical relationship and we keep it on average the same for a given magnitude. That slope changes with magnitude. So that's why you get higher acceleration even for small earthquakes, because of that slope.
Well, thank you, Maha, again. So,
Thank you.